All right, our third presentation tonight is going to be by Hannah Spero. Hannah is a third-year PhD candidate in the Department of Civil and Environmental Engineering and Earth Sciences, and it is advised by Andrew Kennedy at Milhouse Westerick, the College of Engineering. Hannah is an NSF Fellow and involved in the Graduate Society of Women Engineers. Hannah's presentation is titled Storms in Motion, How Wave Forces Drive Coastal Boulder Transport. Hannah, let's take it away.
Time up. Not good. Reset her.
I clicked it.
Click it out now.
Testing.
You're right.
That's it. Imagine yourself standing on a rocky coastline. A towering storm wave is approaching, and it crashes into the bedrock, ripping up a boulder the size of a bus, shoving it across that platform. The sheer power of storm waves is impressive, and these boulders are a record of it. In fact, a relatively unexplored record. And I think we can all agree we find storms, we find hurricanes fascinating. But on the flip side of that, they're destructive. They flood communities and cause devastating effects, especially as coastal populations are drastically increasing. So that's where my research comes in. I'm looking at the forces it takes a wave to move a boulder, so we'll be able to decode this coastal boulder record and protect coastal communities. My work is done over in the Aran Islands of Ireland, where I run a field experiment. And I have three main questions I'm answering. First, when do boulders move? Second, under what wave conditions? And third, can we extend a model of this Ireland boulder transport elsewhere in the world? To answer question number one, I installed sensors within boulders, accelerometers, that log orientation changes over entire winters. Now, what does this actually mean? It means every time the boulders move, we know the timing, and we know if it's lower energy, like sliding, or higher energy, like rolling. Then we can take those timings and move to question number two. What were the wave conditions? And we can use a local tidal gauge that's nearby, and we can use pressure sensors on shore. And together, those showed that storms combined with high tide led to boulder transport. And this is an important finding from my work because previously tidal range was not considered an interpretation of these coastal boulder deposits. And that leads me to my third question, where we want to estimate wave velocities to move these boulders in a model that extends outside of Ireland. And what we found is traditional models use a cuboid boulder approximation, but representing the boulder in true fashion by using iPhone LiDAR scanning techniques, which is a method I came up with, we're able to get a more representative volume. So altogether, this study finds that we need to revamp this traditional model if we want to use coastal boulder deposits to improve coastal hazard management. So let's zoom out to the bigger picture. We're standing here with this towering storm wave in front of us. That's a metaphor. It represents the intensifying storms and hurricanes that are impacting coastlines globally. And it's our job and it's our responsibility to use the tools and our research here, for example, at Notre Dame, to decode these coastal boulder deposits. So we can not just study waves or boulders, which is what I do, but so we can together prepare for storms ahead. Thank you.